Okay, so let's look now at how determinants interact with row operations, or rather, how applying a row operation to a matrix changes its determinant. So suppose that B is row equivalent to A, and it comes by multiplying a row through by the constant K. Let me just change to red here. Then the determinant of B is K times the determinant of A. If B comes by doing a row swap, then the determinant changes by a minus sign. And if B comes by adding a multiple of one row to another, then the determinant is not changed at all. So that makes life really nice. So let's look at an example of how this works. Suppose we take our matrix A to be 2, -8, 4, -2, 8, 9, -1, 7, 0. And we can look at how its determinant is affected by these row operations. So the determinant of A then will be 2, -8, 4, -2, 8, -9, -1, 7, 0. And now these are going to be in straight bars because it's a determinant, not a matrix. So let's see. So first thing I notice is that there's a common multiple of 2 across the first row. So I can effectively just factor that out. So this first row operation that we're looking at right here, what this says is that you can basically just pull the 2 out of that first row and write it out in front of the rest of the determinant. So we've got 1, -4, 2, -2, 8, -9, -1, 7, 0 left inside the determinant. So now I look at this and say, okay, well, I could simplify this somewhat, make it a little closer to reduced row echelon form or whatever. If I were to add a couple multiples of row 1 to row 2 and add one multiple of row 1 to row 3. So I'm going to go ahead and do that, and this is not going to change the determinant at all because I'm using the third part of the theorem here, and this one says that the determinant of B is going to be the same. So I've got my first row just as usual, and then adding 2 copies of this to the second row, I'll have 0, 0, -5. And adding 1 copy of the first row to the third, I will have 0, 3, 2. Next, I'm going to do a row swap on row 2 and row 3, interchange those two. And from the theorem, now I'm using the second part, and it says that the determinant only changes by a negative sign. So now I'll have a -2 out in front of my determinant after doing this row swap. Okay, so now we see that the determinant of A is equal to -2 times this determinant of a matrix which is in upper triangular form. And you're probably asking at this point, okay, so I see how determinants are related to row operations. Well, why would I care? What would I do with this? And so it turns out that if A is a triangular matrix, and it doesn't matter which type, upper triangular or lower triangular, then the determinant of A is just going to be the product of the diagonal entries. So A11, A22, A33, all the way out to ANN. So those ones that go down the diagonal. And maybe I'll just write that here. So this is the product of the diagonal entries. Okay, and so this can also be written in product notation as the product from k equals 1 to n of a sub kk. If this capital pi notation scares you, don't worry, you don't have to know it. It's just the shorthand. It's just like we use a capital sigma for summation, we use a capital pi for products. So to complete computing the determinant, I just take the product of these numbers down the diagonal, because I've got a matrix in upper triangular form, so it's minus 2 times 1 times 3 times negative 5. And multiplying those together, I see that the determinant of this matrix is 30. So this is a very efficient way for computing the determinant of a matrix, way better than that crazy thing with the summation and the sigmas and stuff that I showed you last time.